did a lab where we plotted a position time graph of a car that was moving at a constant velocity. Today what I want to do is look at more position time graphs, the relationships that exist between position and time, and then some numbers that we can calculate from position time graphs. The first thing that I want to do is look at some shapes to determine what relationships hold when I have a certain shape graph. Firstly, we talked about this on Thursday last week when we did the lab. When we have a graph that's titled position time, we know right away which variable is which in terms of manipulated responding. What would position be in this case? What is it, Caleb? Yeah, it would be the responding variable. The responding variable is always listed first, always. And the manipulated variable is always listed second. Now, sometimes it might be position time, sometimes it might be position versus time, sometimes it might be position as a function of time. I'm not fussy in terms of that, in terms of the way you write it that way, but we need to see position first and time second, or whatever the manipulated variable, whatever the responding variable is first, and whatever the manipulated variable is second. Now, on your graphs, the responding variable also goes on the y-axis, and the manipulated variable always goes on the x-axis. The good news is for position time graphs, time is always manipulated, position is always responding, so they're always going to look like this. Now, you look at this particular graph, the first one that I have here, position time graph, what does this straight line represent? What does this straight line represent, Beth? Yes. When you have a straight line on any graph, it represents constant or uniform something. Got it? Now, if you saw a velocity time graph or a force time graph or a power time graph or an energy time graph, whatever, it doesn't necessarily mean constant velocity, but it means constant something. Got it? Straight line means constant or uniform. In this case, it means constant or uniform velocity. Leave a little space in between those two words, actually, because I'm going to come back and add a tiny little thing a little bit later on, okay? That's constant velocity. Let's look at the second one now. What does that represent? Yeah, Art? Yeah, the thing's not moving. I mean, that's still constant, right? Straight line means constant. Constant what? Constantly stopped. You could say constant velocity, but if you said constant velocity, it would be specifically a constant velocity of 0 meters per second. Easier just to say it's stopped or not moving. What's the third one represent? Straight line, right? Straight line. So what does a straight line mean? Constant something, right? Marshall, in this case, it's constant. Yes, it's constant velocity, but it's constant negative velocity. Let's go back and fill in the blank in the first one now. What would that be? Constant positive velocity. Now, understand what that means. A positive velocity means you're going at the same speed, uniform motion, but going forward. Negative velocity means going backward. If I'm driving towards Calgary and I define north as positive, then that's a positive velocity. Coming back is a negative velocity. Coming back, it doesn't mean necessarily that I have to drive my car in reverse. Right? I'm not backing up from Calgary to Okotoks. It just means that I'm going towards Okotoks, going in the negative direction, right? So this is going towards Calgary with your cruise control on. This is coming back from Calgary with your cruise control on. This is sitting in the drive-thru at McDonald's waiting for your double Big Mac with extra patties and bacon on it, or whatever it is that you're going to order. Who would order that? What's the fourth one mean? Position versus time, Art? Acceleration. Yeah, this is a curved line, right? So that's not constant something, right? That's changing something. But you can see that the slope of it is increasing. It's getting steeper and steeper and steeper. So what's increasing? Well, the slope of this represented velocity. So this means that it's velocity, but an increasing velocity. The easiest way to say an increasing velocity is to say it's accelerating. Accelerating. What's the last one mean? Yeah, that would be a deceleration. Or we could say a negative acceleration. This would be a positive acceleration, and a deceleration is still an acceleration, but it's a negative acceleration. Make sense? Well, let me give you another one that I didn't put in here. Okay, see if you can get this one. How about I drew a position time graph that looks like this. This is a tricky one. Who's got this one? Position time graph that's a straight line going straight up. Who's got it? Marshall? Okay, there's no change in time, but what does that mean? Sorry? Oh, it's impossible, right? This is like a wormhole or something. This is not like, this is a trick question. You can't change your position from 0 to 20 or whatever the position is with no time going by. Hey, Marshall, you're right. You said no time has elapsed, right? No time has gone by. You can't go from one place to another, not in everyday world at least, from one place to another with no time elapsing. So that's a trick question. I wouldn't give you this on a test, okay, because it's a trick question. What about this one though? This one's better. This isn't going from one place to another with no time. Time is elapsing here. What about this one? Like, just think about it, right? Don't try to just start off an answer because it seems to follow a pattern or something like that. Like, look at it and try to determine what's actually happening here. Yeah, Aaron? Two objects moving at the same time? No. Same object, represented by the green line here, and then right here. What's happening, Beth? Change in direction, so we're going forward then backward. Good guess, but nope. Aaron? Yes. This is a trick question as well. Look at what's happening here. You're going at a constant velocity, right? Right? Increasing position, right? Going at a constant velocity. Then what happens, Aaron? You're going back in time, right? The time is getting smaller, smaller, smaller. So if this was 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds, you're going back in time 4, 3, 2, 1 seconds. Which, as far as we know, well, as far as most of us know, you can't do. Okay, if there happens to be somebody in this class that's from the future, and you know you're from the future and just not telling anybody, well, then you might know that this is possible, but the rest of us at least have to go with the assumption that this isn't possible, because as far as we know, we can't go back in time. Make sense? Okay, so that's a trick question as well. I'm not going to give you a trick question on the test, I promise. I just give you them today to just make you think a little bit, all right? Okay, let's take a look at what we have down below these different shapes here. What I want to do now is actually determine something from these graphs, right? Get a measurement from these graphs or a calculation from these graphs to determine significance of one thing or another. How do you think I would find the position at a specific time on any of these graphs? I'll give you a hint. None of these are trick questions, by the way. I'll give you a hint. Finding the position on a position time graph is not hard. Right? Yeah. But what part of the y-axis? Okay. So essentially what you're saying there, without actually saying it, is you want to go up and over. So if you want to find the position at this moment in time, go up and over and look at the y-axis at that point, right? So let's write down here for position, we're going to go up and over on the graph. Good? In a couple of days, you're going to see velocity time graphs. How do you think you're going to find velocity on a velocity time graph? Up and over. How do you think next year in Physics 30, you're going to find force on a force time graph? Up and over. How do you think you're going to find momentum on a momentum time graph? Up and over. How are you going to find energy on an energy time graph? up and over. Whenever you want to find a variable that appears on the y-axis, you're just going to go up and over. Got it? Including on a position time graph. Now, what did we define displacement as? You remember that? It's only been a week. It was a week ago today, actually. No. That was speed as distance over time, right? Change in what, Kem? Change in position. Good. So if you want to find displacement on a position time graph, you know how to find position, right? So how do you find the change in position? Kem? Marshall? Yeah. Yeah. It's the final, no, not final displacement, final position minus initial position. In other words, it's up and over times 2. Up and over, and then you got to subtract the 2, right? That make sense? To find the final position, let's say on the first graph here. Here's my final position. There's my initial position, and then you got to subtract the 2 of them. Now, finding the velocity. The velocity on a position time graph. I'm going to create some more space for this one. I'm going to go through an analysis here to figure this one out, because this isn't just a simple up and over. We got to actually calculate something. But what exactly we're going to calculate? And you might remember, to be honest, you might remember from Science 10 what you're going to calculate here, because your Science 10 teacher would have told you. But we're past that now. We don't need to be told how to calculate something. We're going to figure out how to get something from any graph, a position time graph or any other graph. Okay, that's what I want to show you here today. What's the equation for this graph? Y equals mx plus b. Do you guys remember that? From Math 10? Or Math 9, whatever it was. I think you learned it in Math 9 first. Y equals mx plus b. I want you to write that down. Does that make sense? Y is your y coordinate. M stands for what? Slope. X is your x coordinate. B stands for the y-intercept, where it crosses the y-axis. Where does it cross the y-axis in this one? 0. So generally, that y-intercept is 0 here. It is in this specific case, at least. Okay. The y-axis is position. Actually, you know what? Let me just change this a little bit. Y-intercept isn't 0 anymore, is it? Okay, so what's the y-axis? Well, whatever I'm reading off of the y-axis would be my final position. Okay, y-axis is position, right? What's m stand for? You guys just told me that a second ago. Slope. I'm going to write the word slope in here. Okay, I want to get in the habit of that, because as we go on in Physics 20, sometimes mass means something, right? And I don't want to get mixed up with the symbol m for mass and the symbol m for slope. So I'm going to change it to the word slope. X is, that would be time, right? B would be, what would B be? The y-intercept. What is it? Yeah, it would be the initial position. We're going to call it di. Good? I'm actually going to take this over with subtracting and say df minus di. I could say t or delta t. I'm going to call it delta t, actually. Makes it work a little bit better for me. df minus di is delta d is equal to the slope times t. Hey, what equation have we learned from our data sheet? It's on our data sheet that has d and t in it. Well, there's only been one. We've only learned one equation. Which one is it? Yeah, velocity is equal to displacement divided by time. Let's rearrange it to solve for displacement, because that's what I solved for here. Displacement is equal to velocity times time. Let's Let's cross off displacement because it's in both. Let's cross off time because it's in both. What are we left with? What are we left with here? Xander, what are we left with here? Slope. What are we left with here, Xander? Velocity. So what's the slope equal to? Yeah. Now, you might have just remembered that from Science 10, but in Science 10, you were just told that the slope is equal to the velocity, right? You might not even remember that, and that's okay. Now you know why the slope of this graph is equal to velocity. So let's go back to that last page and fill in the blank there. The average velocity is the slope of the graph. You guys remember how to find slope? Rise over run, yeah. How many people have seen it in math classes, the words rise over run? How many people have seen it this way? Delta y over delta x. Okay, how many people have seen it as y2 minus y1 over x2 minus x1? Okay, these all mean exactly the same thing, right? How else could we write it now? What's y2? Well, that's position 2. y1 is position 1 over t2 minus t1. In other words, we could write it as displacement over time, right? So however you want to find the slope of this graph, I don't care. Using rise over run, y2 minus y1 over x2 minus x1, displacement over time, I don't care. Okay, they all mean the same thing. What does the word instantaneous mean? Yeah, at a specific point, right? What's the instantaneous time right now? It's 9:24. That's not the interval of time. That's what time it is at this moment. You want to find the instantaneous velocity, the velocity at one moment in time. Well, if the slope, if it's a straight line, here, let's say, if it's a straight line, then the velocity is constant, right? And if the velocity is constant, then we would say the instantaneous velocity is just equal to the average velocity. I mean, think about that. In this first graph here, if we find the average velocity to be 10 meters per second, and it's 10 meters per second all the way along there because it's constant, then what's the instantaneous here? 10. What is it here? What is it here? Right? If it's a straight line, then the instantaneous is the average. If you have multiple straight lines, like something like this, well, you'd have to find the slope of each straight line, right? To find the average of each interval or the instantaneous anywhere along there. And if it's a curved line, we won't deal with that yet. That'll come later on, tomorrow. I want to take a look at an example that we have here, example number 5 in your worksheet booklet. It says, use the following information to answer the next 5 parts of this question. So just an A, B, C, D, E part of this question. You can see that this is a position versus time graph, although really, by all rights, there should be a title for this. We always should have a title. The title would be position versus time, position dash time, position as a function of time, whatever. Responding versus manipulated, y-axis versus x-axis. You can see that the direction that we have given here is east. These are all positive numbers, so we don't even need to technically write in positive is equal to east because it's assumed that positive is equal to east. It's labeled as east, and the numbers are all positive. So positive is east. You want to write it in, go ahead, but it's not the end of the world if you don't write it in. If it said on the y-axis position in meters to the west, well then we would just, by default, make west positive. Does that make sense? Because those numbers are all positive, and if it was west, it would mean west is positive. All right, what does the shape of this graph mean? We're not asked that in A, B, C, D, E, but what does it mean? We just went through that, right? So what does it mean, Marshall? Yes, this is constant negative velocity. So we're going backwards at a constant velocity. Doesn't mean going in reverse. You haven't put your car in reverse and then set on cruise control. I don't know if you can do that or not. Probably not. I'm guessing you can't put your car in cruise control when it's in reverse. I think I have something to try now, though. I don't think that would work. I'm sure that it's got to be set to not work, but that's not what it means, right? It means we're going in the negative direction. We may very well be driving forward, but driving forward in the negative direction. So in this case, the positions are all positive, but if we start off in Calgary, which is a positive position, then we go to De Winton, which is still a positive direction relative to Okotoks, and then we're back to Okotoks, which is still a positive direction. We're in the positive direction the whole time, but we're moving in the negative direction. Got it? So we're north of Okotoks, or east of Okotoks, whatever, the whole time, but we're moving back towards Okotoks, a negative velocity. Okay, let's find some things from this based on what we just looked at here. What's the position of the object at 10 seconds? You guys remember how to find position on a position time graph? Up and over, yeah, up and over. Velocity on a velocity time graph was up and over. Force on a force time graph is up and over. When you want to find something on the y-axis, go up and over. So let's go over to 10 seconds here. 10 seconds, go up and over. Up and over, that looks to be, what is that? 30 meters per second. Sorry, 30 meters, I should say. Now, should we write in east there? It doesn't matter. It's okay to write in east, but you don't need to write in east, because if you put positive 30, then the positive means east with the way that it's already defined as being east positive. What's the displacement of the object between 0 seconds and 10 seconds? Change in position, right? That's df minus di. What's my final position between 0 and 10 seconds? 30 meters. What's my initial position? 80 meters. What's my change in position? 50? Negative 50 meters. What's the negative mean? West. I went west, right? It doesn't mean I'm at west. I'm still east of Okotoks, right? I'm 80 meters east of Okotoks. Now I'm 30 meters east of Okotoks. I'm still east of Okotoks, but which way was I going? West. My displacement is to the west because I'm less east of Okotoks. I guarantee you that when you get this question on a test, and you will get this question on a test with different numbers, right? I guarantee you that some of you are going to write that in as positive 50, or at least whatever the numbers on the graph give you, right? You're going to forget the negative. And guess what that's going to get you? Half value. It's something. You kind of knew what you were doing, but you're not going to get full value because that negative is important there. What's the average velocity between 0 and 10 seconds? What's the velocity, the average velocity equal to? The slope of the graph. I like to calculate the slope by just saying displacement over time. That's what it is, right? Rise over run, delta y over delta x, y2 minus y1 over t2 minus t1, displacement divided by time. Same thing. I like to write it like this because I already found the displacement. It's 50 meters. The time is 10 seconds. Is that 5.0 meters per second? What does that get you for a mark? Half marks, right? What am I missing here? Negative 5.0 meters per second. Or you could have, I suppose, said 5.0 meters per second to the west, yes. But I think it makes sense to say negative here. The instantaneous velocity at 2 seconds. It's constant, right? It's negative 5 the whole time. So what's the instantaneous at 2 seconds? Negative 5. What's the instantaneous at 6 seconds? Negative 5. What's the instantaneous at 9.3 seconds? Negative 5. It's not changing. So the instantaneous has got to be the same as the average. 7 seconds? Negative 5 meters per second. Good? It's not crazy hard, is it? Now, in a couple of days, we're going to look at velocity time graphs. They look a lot the same, and some of the ways we do things are similar, but it does get a little bit confusing then, not because velocity time graphs are hard or position time graphs are hard, but we look at them and sometimes get them mixed up. Right? They're both relatively straightforward, but we sometimes get them mixed up. So it's important, really important right now that we internalize this and that this really makes sense to us so that when we get to those velocity time graphs, we're less likely to mix the two up. All right? All right, here's what I want you to work on now in class for the next bit here. Worksheet number 3. You're going to love this. Listen carefully. Which questions I want you to do. Number 1, write these down. Number 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Worksheet number 3, for now, questions 1 to 10. Let's have a look at 1 through 5 right now. Question number 1 says the position at 7 seconds. As I was walking around, a couple of people have defined east as positive here. I wouldn't do that. It's not wrong to do that. I just wouldn't do that here. If they tell me in the question, or if I tell you in the question, that we're going to the west, and all of these numbers are positive, we're making west positive. That make sense? Like, go with the convention that's already given to us there. You might as well. It's not wrong to make east positive, but it's just going to get confusing. I'm telling you, just go with what is given to you. So west is positive. You don't need to write that down, though, because it's already written down effectively that west is positive. What's the position at 7 seconds? I'm just going to go up and over, right? Careful here. This is 6. This is 8. This would be 6 point, what, 6.1? 6.2? Nope. This would be 6.4. 6.4, 6.8, 7.2, 7.6, 8.0, right? 7.0 would be right here, right? Does that make sense? You got to watch those intervals on the axes. Go up by 0.4 this time. Go up and over. What's the velocity at that point in time? It's going to be 30 meters. Do I need to write 30 meters to the west? No, I don't have to because west is positive. It's assumed west is positive, right? What's the displacement between 0 and 5 seconds? Well, the displacement here is final minus initial. The final position at 5 seconds, if we go up and over at 5 seconds, the position is, this is 4.4, 4.85. We go up and over, oh, it's 30 meters. The position at 0 seconds is 0. So we're going to say it's 30 meters minus 0 meters is 30 meters. Okay, nothing really to show for question number 1 for work, but there is work to show for question number 2, right? A little bit. The average velocity between 0 and 5 seconds. How'd you guys find it? Rise over run? How many people did rise over run? Okay, good. How many people did delta y over delta x? Okay, how many people did delta d over delta t? Displacement divided by time. Yeah, it's the same thing. It's all the same thing, right? I'm using displacement divided by time because I already found the displacement. 30 meters divided by 5.0 seconds. That gives me 6.0 meters per second. Ooh, this one's tricky. The average velocity between 0 and 9 seconds. Between 0 and 9 seconds from start to finish here. Well, there's a couple of options you can do here. You can draw a line from 0 to 9 seconds and say rise over run, right? Or delta y over delta x. Or what's the displacement between 0 and 9 seconds? 30 meters. What's the time? 9 seconds. 30 divided by 9 is 3.3. By the way, we don't worry about significant figures with graphs. So if you said 3.3, 3.33, whatever, we're not going to lose any sleep over that. What's the instantaneous velocity at 3 seconds? At 3 seconds. Do not, please do not do this. Say, oh, the position is this, the time is this, divide those two. Don't do that. It's delta, right? You can't just take 1 point and divide those two. So what you're going to do here is say, look, the average velocity between 0 and 5 seconds was 6 meters per second, but yet it's constant. So what's the instantaneous velocity at 3? 6 meters per second. What is it at 2.5? 6. What is it at 0.5 meters per second? 6. What is it at 4.9 meters, at 4.9 seconds? 6 meters per second. And the instantaneous velocity at 8 seconds, don't make this one harder than it has to be. At this point right here, at 8 seconds, what's the shape of that graph? It's a flat line. Ken, was that you that said that? Yeah? It's a flat line. What does that mean, a flat line like that? It's not moving, right? So what's the instantaneous velocity? 0 meters per second, right? Good? Good? All right. Let's continue on 6 to 10, okay?